We're going to introduce subsidence, tile drains, and some wells for pumping, and some elements for recharging. Wait. Okay, so we are basically introducing a tile drain along these nodes here. And then any flow that is collected by these tile drains will be taken out to a stream node 20. So all the water that is collected by these tile drains that are lined up with these nodes are going to be put into stream node 20. We are introducing 1, 2, 3, 4, 5 wells. Right, so you can see that you can have your wells aligned with nodes, or they don't have to align with nodes. And we're going to use these 5 elements as recharge. So one thing you have to be careful about when you're populating your pumping rate file that you'll be working on, since we're dealing both with recharge and pumping is simulated with a negative value. So a positive value really means recharge, a negative value means pumping. And we are also going to introduce subsidence in this example. And the subsidence parameters are also given in page 21. So let's go ahead and, yeah.
Drains, is there a way to turn them on and off, or do they have to operate the whole simulation?
They operate the whole simulation. If the groundwater head goes above, they come on.
You can't, if your simulation period's 50 years and the drains were installed at year 25, you can't.
Yeah, good question. No, yeah, we can't do that. Yeah, that's actually a good question.
We ran into that and we couldn't figure out how to deal with it. I guess.
Yeah.
A secret way or something.
There isn't. I mean, yeah, they're supposed to be there. That's a good question. We do that with the diversions and whatnot, right? We can actually turn on and off just because of the diversion rates. And also we are going to see with the adjustment, we have a supply adjustment feature. We can do that with the diversions and pumping, but not with the tile drains. So one question came up with this file, which is the irrigation fraction file. So with the water supplies, be it diversion or pumping, what we normally do is you have to specify, okay, here's the water supply, diversion, pumping, but what are you doing with that? Are you using it for agricultural purposes or urban purposes or both, and in what fraction? So irrigation fraction is how much of a particular supply you're using for agricultural purposes. So in this particular example, we haven't built the land surface feature yet. So we are pumping the water and sending it outside, but the model still expects to have something in that line. So we're just, providing that information saying that, well, whatever we pump, let's assume that's for ag, but in reality, we are just sending it outside. It's just, one of those things that you have to provide even though it's not going to be used. One question came up about, like possible ways of specifying pumping. So here in this case, we say, okay, the total pumping from those 5 wells is 70, and we are using this ICall WL and frac WL parameters to distribute the 70 equally between those 5. But you can also set, if you have the data pumping individually for each of those wells, in that case, you would actually have, 5 different columns of pumping here, and then you would set this parameter to 1, 2, 3, 4, 5, right? And you can do the same thing with recharge. If you have the, like recharge values for each of those recharge locations separately, you can also have, 5 different recharge columns, and then you would also do the same thing. And in that case, you can basically set this, you can keep this fraction parameter as the same because, there's only one column going to each pumping. So there are different ways of doing this depending on the type of information you have in your hand.
this Elm from specs one, so this is for the recharge portion. So here, when you're the destination.
Okay, so yeah, that came up
it-
too. So, this is actually, these two parameters are not really used.
Oh, they're not.
Yeah, so it's just, it's recharge. This water is coming from nowhere, right? It's just appearing.
Okay.
But the model is basically expecting to read this many numbers of data, right? So you just enter something. You can actually
Okay.
enter anything here for these
So
two
those are-
columns.
okay, those are-
Yeah,
Okay.
yeah, yeah. Let me mention that too. Okay, so this question came up twice. So let me mention that too. So this is the how we specify the recharge, right? These are the elements that we are using for recharge, and here's the destination type, right? So and then the destination ID. In this case, I set it destination type 0, which means that I'm taking that water outside the model area. But this is recharge. It's actually coming in to the model area. In the recharge case, these two variables are not actually used. The model still expects to read however many columns of data here, but since it is recharge, it's not actively using these things. So that recharge water is actually appearing from nowhere and just coming in. So effectively, you can set these two variables to anything you want, and the results should still be the same because you're not really taking that water to anywhere.
Just a follow-up question on that. So in this case, you don't have the choice to specify the
So-
unit conversion if that involves with time, right?
Correct,
So-
because it will figure out from there.
Right, but you also mentioned that if you only given like one number, So
Which
say-
now your pumping is constant throughout the,
Right.
yeah.
Right. So if that's the case, say I do constant pumping all the time, then do I specify that here?
Yeah,
Or-
in that case, you have to make sure that, so now you're dealing with, well, whatever it reads there, you have to make sure that it's a cubic feet per day.
Right.
Right?
Okay.
So you have to set this properly so that both the time and the spatial conversion are actually built
In
into
this
that,
one,
into
in
that,
this one.
yeah.
Okay, because in other cases you have a separate item for the temporal unit conversion.
Yeah, those are basically static parameters like hydraulic conductivity and stuff like that. I'm just telling, okay, what is the spatial unit, what is the time unit, so that, if you're giving your hydraulic conductivity, let's say, feet per month, it will automatically convert to feet per day for a daily run.
Right. But in this case, we don't have that item, so you have to combine it into this conversion
Yeah.
factor right here.
Yeah, and make sure this is other way around. This has to, you're going from TAF to cubic feet, so this has to be 43,560,
Oh, yeah.
and then 3 more zeros. Wait, do I have an error in my? Oh, but this is just an example.
That's probably not right? Acre
Yeah,
feet.
yeah.
So this
See,
one is
okay, I need to correct that. Oh, yeah,
Gotcha.
that's an error. I'm sorry. I actually corrected it in the input file templates that you download. I forgot to correct it in these examples because somebody mentioned that last year. So let's talk about this time series data a little bit more. So what the model does, we're looking at the pumping rate here. What you're giving in this file is, again, you have 2 columns of data, and you're converting the spatial unit of your pumping rate from 1,000 acre-feet to cubic feet. And then the model, when it reads these data, it realizes that this is monthly interval. So it figures out that this is 1,000 acre-feet per month, right? And then since you're running a daily model, it automatically converts to cubic feet. First, it applies that conversion there, converts it to cubic feet per month, and then internally it figures out the number of days in the month and converts that to cubic feet per day. But let's say that you want to have a steady, constant pumping rate throughout your simulation period. In that case, you would do something like this. Let's comment these out. Wait. 1 second, guys. Okay, so let's say you enter something like this. 10, or let's do this, 12, 31, 2,000, 2,500. Okay, let's say you want to pump, constantly 70 and then recharge constantly 40. Now the problem here is there's only one line of entry here, so the model will not figure out the time unit of this. Well, it's 70, but 70 what? Is it monthly? Is it daily? So in that case, you have to make sure that both your spatial and temporal conversions are all built into this one here. So in this case, this is doing the conversion from TAF to cubic feet, but it's still keeping it monthly. So you would have to actually divide this at least on average by 30. So now you're not only converting the spatial unit, but you're also converting the temporal unit to make sure that you're entering cubic feet per day. Does that make sense? Because with a single entry, it just doesn't know what your temporal unit is. Is it monthly? Is it daily? You have a question? Yeah.
No, I think you just explained something I had a question about earlier.
Oh, okay.
The spreadsheet says that it's in 1,000 acre-feet per month, right?
Yeah.
And so where is that accounted for? Where are we
The month
telling
part?
it? Yeah.
The month part is in the data itself. We are giving it month by month,
Right.
so it knows it from there.
Okay.
So it knows that it is. I mean, it doesn't know, but it converts that to cubic feet. But the temporal one, it knows from your timestamps because you're giving it, October, November, whatever. So it's okay, this is monthly, and then converts it to daily. If your time interval is daily, so you have 365 days, then it will know that if it is daily. But if you're entering it in a way that it's constant, that I just showed, right, 2,500 year, 2,500, whatever, then it doesn't have any way to figure out if it is monthly or daily pumping. Then you have to make sure that all that conversion is in that factor up there.
Okay.
Make sense?
No, the last part doesn't make sense.
So-
if you use 25, you get
Okay.
2,500.
So let's say that I want to pump, here, let me, So let's say that I want my goal is to pump 70 TAF per month, right? 70 TAF per month throughout the entire simulation period, never turning off. Okay? So then I would basically say, okay, just give a large enough date
Right.
that covers my simulation period, right? So that's what I would do, minus 70. Okay. But the problem is, so this is per month, right? But I'm running a daily model.
You're not doing, okay, I see what you mean.
Yeah, so
You
so it
had
just
a
doesn't
fixed
know.
rate,
Yeah.
You might just enter this one time.
Yeah.
And then it wouldn't know the unit.
Yeah, the timing. Is it monthly, daily? Yeah, then you would have to build that conversion to that factor.
So in some of the other input files where we say 1 day or,
Yeah, so those are all properly done. I mean, suppose at least in the complete, like the 1,000 CFS, where, you know, the flow that is coming in.
right?
If you go back and look at it, that conversion factor, it's already cubic feet, but that conversion factor is now not for the spatial part of it, but it's for the temporal part of it. Now it's converting the seconds to days, which is 86,400. Yeah, I know. I have to sometimes think about it too.
So I think this might be the case, but I just want to confirm it. So you have the pumping from well, and then you specify this this file for the well specs, and you have the recharge from this the element. You specify this. Can you do it like in the reverse order? Like can you recharge to the well and pump from?
Yeah,
the
yeah, yeah,
elements?
yeah. You can use both wells and elements for pumping and
or
recharge.
Okay. But
Yeah,
if
yeah.
you have to do.
But to be honest with you, I can't remember how your vertical distribution would be. I think it would be just like the Coseni equation. You know, it would.
Okay. Okay. So I'm just thinking, so if you want to use the same set of wells for both pumping and recharging.
Oh, you have to then specify them separately, as if two separate entities.
Okay.
Yeah.
Okay, that makes sense. Thanks.
All right, I see. Okay.
How come I am in simulation
Okay.
mode and complain about this?
Results debudget.bin must be in. Okay, so apparently when you created your, are you running the budget?
Not yet.
Not yet. Okay. So the somewhere that Z budget, it can't have a .bin. It's expecting an HTF5 file output,
I
right?
see, yeah.
So it has to be HTF. You know. So
Yeah,
I
tried
can't
to
remember.
find- Yeah, I tried to. Yeah, no.
Yeah, you can do a search, I guess. You know, TextPad allows you to do searches over all these parameters. But yeah, one of those output, instead of .bin, it has to be .htf.
Okay, I see.
Because it's a negative, so if you add up all the negatives, so it's already, yeah. So there we go.
I think I got my conversion wrong.
Yeah.
Okay, so
Because it
meters.
says,
Okay, feet to feet. Why is it 2? It should be 1. What file is this? Well spec. Okay.
I thought that was already populated, no?
Maybe
The
maybe
last
I
one.
did it wrong. It's very possible.
Where am I? So here, okay. All right, so that's done. Let me try it again.
Okay, well, 1 is outside the model domain. Okay, let's look at the coordinates. Okay, hold on. Meter to, is that the, isn't it
maybe that's-
328 something, 2808? Is that what it is? Yeah, something like that. You might want to look at the,
That's right. Okay.
all right, let's see if this is going to run. Okay, let's look at, it's very possible that you forgot to delete the percent signs. 5, yeah.
Nice. Okay, thank you.
Mm-hmm. Okay, all right, so results, Z budget bin. Okay, so let's go to, I think maybe this is my fault here. Maybe I go in there, simulation. Groundwater main.
Oh,
Let's try look at groundwater main. Go down a little bit. Okay, right here. So, yeah, that's my fault. That I guess
it should be
is the HTF.
HDF.
Mhm. Let me see. It's possible that I forgot to change. Is it running now?
Yes.
Okay, so that's, I forgot to change that. Huh, okay.
Two questions. I think you got my first one, which was
Okay.
in your template.
Okay, yeah, I'm sorry.
The second one is, how did you use this to import an all streams file? Like, separate for each reach? How did you get the one?
The whole thing.
Yeah.
So in Excel, what you need to do is just go to any sheet,
Okay.
okay? So first, so each of the reaches, the names are reach 1, reach 2,
Right.
reach 3, right?
Okay.
So go to any sheet and so like create a title, let's say all streams,
Okay, got it.
right? No, I'm sorry, in the cell itself.
In the cell. All right.
Okay. All right. And then underneath, just, list those, reach 1, reach 2, reach 3. But make sure that they are, yeah. Okay, now open up that budget tool again, the import tool. All right, so point to the stream budget. Mhm.
Okay.
Okay, click on the data import by location group. Now select all, including the title.
Okay, got it.
All right, and then you can choose all or some.
Okay, so import that, got it, and that all
Okay.
comes in, and that
Yeah.
takes care of the inflow outflow.
Yeah, exactly.
Okay.
And then it uses that title as your all stream. So if you forget the title, then it will use reach 1 as a title and only
Okay.
add reach 2 and reach 3.
Okay, got it, thank you.
That's all right?
The same question someone was asking. So this is to convert from 1,000 acre feet to cubic feet, and the conversion from month to day. Where is it done?
It's done automatically. So looking at this timestamp, the model knows that your input is monthly, right?
Okay.
So this is 70,000 acre feet per month, just looking at the...
So because we have here
Yeah.
November, okay.
Yeah.
So anything here, it puts this volume over the difference
Yeah.
between these two time steps?
Yeah.
Okay. Okay.
Yeah. So I guess I made a mistake with one of the input files. If it tells you that zbudget.bin should be a HTF5 file, make sure that that bin is converted to HTF. Some people are running into that. So I guess I forgot. Did you guys run into that too?
Yeah.
Sorry, there's enough frustration, right? Punching in all these numbers, and here I am giving you more headache.
We thought it was an intentional little You're feeding us.
Trying to see if you can catch my error, yeah. So let's, 15 minutes, just quickly look at the budget files, some of the new columns that are now populated, go through the results, and then we'll go to lunch. So let's see, complete. Okay, so let's go to the groundwater budget, and what I want to show you is that now we have, since we are now simulating subsidence, we got the subsidence column going. That's non-zero. Again, since we're talking about expansion and compaction of these interbed thicknesses, sometimes we have positive subsidence, sometimes negative subsidence. Negative means these interbeds are now expanding and they're sucking water from the aquifer material like sponges. Positive means they're actually collapsing and they're releasing water from their own matrix into the aquifer. And then we have the tile drain here now, and you will see that has to be always a positive value, which is negative here. That means it's an outflow. All right, and you can see the same thing in the stream budget. If you look at the stream budget, I believe for Reach 3, let's go to Reach 3. There's the tile drain appearing now. So we are basically taking water from one system and putting it to another system. Okay, now let's look at the results quickly. So this is our animation for the groundwater. So these are our pumps here. These are the recharge operation going on. Our spreading basin is doing a great job building up the groundwater elevations. You can see this little dip here, which is where we put our tile drainage. And essentially, as we are increasing and decreasing the pumps, the groundwater elevation is going up and down, up and down. And here, apparently, our groundwater is gaining from the stream. And somewhere around here, we are right next to the stream. It's hard to tell, but I don't know what's really happening there in terms of stream aquifer interaction. All right, so as part of this example, we also created a velocity vector to be used by TechPlot. So I basically processed that with TechPlot. So, the arrows kind of give you the direction of the groundwater flow, but the magnitude of the arrows are not related in this case to the magnitude of the velocity, because I tried that, the magnitude was changing all over the place. I just couldn't get it to make sense. It's just, it makes sense magnitude-wise, but just didn't look nice in the animation. But overall, you can see what's happening. We are building our mound here, so our flow is kind of spreading out of that mound. These are our pumps going on here, and the flow is towards those pumps. And our recharge elements are here. Again, our velocity field is radiating from those recharge. And right here should be our tile drain, where groundwater is flowing into the tile drain. So my goal is to eventually, either me or somebody will develop a transport model, and we'll feed this information into the transport model and hopefully do some water quality related simulations. So I want to show you the stream aquifer interaction and how it gets affected by this recharge and groundwater pumping operations. So again, don't look at this very initial part of the graph. Again, this is because of our bad initial conditions. The system is kind of stabilizing itself. But here what we're looking at is this orange line is the recharge. right? So this is basically our recharge from our bypass. And this guy is here are those 5 elements that are recharging. And the reason why I see like this castle wall looking effect is because, we are saying, okay, monthly recharge is 40 TAF, but it is getting distributed to daily. Some days, some months are 30, some months are 31. So that actually changes the daily rate a little bit. And that's why you see that castle wall effect. So recharge, and this guy right here is the pumping. Okay, and the green line is the stream aquifer interaction. So what is happening here is when the pumps come online, start pumping, the gain from stream increases. Basically, groundwater elevation is decreasing. We're pumping right along the stream, so the stream starts losing. When the recharge operation starts, basically that loss from the stream quickly drops, but then the pumps come online again, our stream starts losing. When the recharge happens, they start losing less and less and keeps continuing. And that's basically kind of the meat of these studies with the water transfers, like we heard Mesut yesterday switching from diversions to pumps, but are you really pumping groundwater or are you pumping stream flows? Lake groundwater interaction is pretty much the same here. Again, these castle walls are recharge. These guys are pumping here. And anytime you pump, what is happening here? Gain from groundwater. Okay, so the lakes are losing to the groundwater. Anytime you recharge, the lake is gaining from the groundwater. So with the pumping and recharge, you're affecting your lake and storage and stream flows. This is just, again, a cross-term check for the tile drains. From the groundwater budget, this is what I see in terms of flows to tile drains. And from the stream budget, this is what I see. So what I take from the groundwater is actually get put into streams. So again, I'm making sure that I have global mass balance. When I'm taking water from one system, I'm making sure that I'm putting it to something else so that I'm not losing any water. Subsidence, you can also create a tech plot output for subsidence. That's what we did here, and create animations for the subsidence. This is in terms of thickness now, how much compaction is happening. So right here where we are pumping, we have large subsidence, and here where we are recharging, our subsidence is negative, meaning we have actually expansion. Same thing here, where we are doing our spreading operations. Basically, we are expanding those sponges. And how overall subsidence in the entire model area gets affected by the net recharge. So I basically added all the inflows from the recharge operations and the spreading basin up north and subtracted the pumping operation. So I have a net recharge here in this red line. This green line is just to make sure that this is the zero line for the net recharge. And the blue line is my cumulative subsidence in terms of acre feet. So this is the volumetric amount that is getting added to the aquifer system or taken out of the aquifer system. So when we have a net large recharge, our subsidence quickly decreases, right? So basically, the system, those interbeds are sucking up water from the aquifer. And when we start pumping, our subsidence increases. When we recharge, decreases. But overall, there's kind of a trend going down, basically subsidence decreasing overall, because if we are recharging more, with the spreading basin operation up north and our recharge wells, we're actually in effect recharging more than we are pumping. So overall, we have less and less subsidence going on over time. So I also want to quickly look at some of the specific nodes, locations, just for the subsidence. So we are going to look at the subsidence right at this node, right next to the recharge element, and how the recharge is affecting. So a negative subsidence is actually the opposite of the subsidence. Actually, the system is bouncing back. Those sponges are increasing in thickness. So this up and down pattern here really shows the recharge pumping operation. The recharge comes online, and my subsidence decreases. Pumping comes online, it increases. Recharge comes online, it decreases. And you see this staircase effect here because of the number of digits that we print out to the output. We use 4 digits, but turns out that the difference is actually in the 5th, 6th, 7th digit number. So we are not capturing that. So you see it's as if like a staircase effect. And then we are going to look at a node right next to this pump here for subsidence. And now this is the opposite. As the pump comes online, my subsidence increases. When the recharge away from the node comes online, it decreases a little bit. Pump comes online, it increases, decreases. But it seems like there's overall kind of a asymptotic behavior here. It seems like it's going to stabilize, somewhere around here if we kept running this model. Yeah.
What's the accuracy of this model with this?
It's very accurate. What do you mean?
Well, you're showing like 3/1000ths of a foot. I don't even know if you can measure that.
No, you can't.
Or is this just using
yeah, this is just an example. You can't really measure that, but it's probably related to the parameters that we put in. But when we actually calibrate our models, we try to look at the measurements, and they are definitely not. So this is just a numerical effect, basically. Yeah. But other than that, as I said, it is very accurate for sure. And finally, we are going to look at this node. So there's no, pumping or recharge happening nearby, except there's a stream here. And if you remember our animation, it looked like the groundwater is gaining here from the stream. So we are going to look at the subsidence right there. And again, sure enough, our very accurate model is giving us subsidence values in the 5th digit, and they're negative. So that means that there's actually, the sponges are actually, again, expanding because the stream is losing, so groundwater elevation is increasing. So overall, we have a negative subsidence, and it basically stabilizes at this, this tiny amount here. All right, so I think it's lunchtime. Yeah, so